All right, let's get right into it. For anyone who's serious about battery manufacturing, you know it's about so much more than just the chemistry. We're going to go way beyond the basics today and explore what is the single most critical step in the whole process. It's where a battery's potential is either fully realized or, well, permanently lost. I'm talking about the art of electrode coating. This is it. This is where the blueprint becomes reality, nanometer by nanometer.
And that quote, it really hits the nail on the head, doesn't it? This is the fundamental challenge. This isn't a step where you can just compensate for a mistake later on down the line. The quality of the entire battery cell, think about it, its performance, its safety, its entire lifespan, all of it gets defined in these few critical moments of laying down a perfect film. Any mistake you make here is locked in forever.
So how do engineers actually tackle this massive challenge? Well, they don't just have one tool. They rely on a whole toolkit of different methods. And the choice isn't random. It's a really strategic decision. It's based on things like line speed, the slurry's rheology, how it flows and behaves under stress, and of course, the insane level of precision you need for the final product.
And this table, it lays out the core trade-offs just perfectly. You've got slot die, which is really the gold standard for high-throughput mass production. Then there's the comma bar, which is more of a flexible workhorse, especially good for those trickier, high-viscosity slurries. And then you have gravure, which is all about ultra-high precision, maybe for very thin or specifically patterned coatings, though you see it a bit less for standard electrodes.
Okay, let's dig into slot die a bit more. The big thing to remember here is that it's a closed system. We call it pre-metered. All of its precision comes from directly controlling the volume of slurry being pushed out by a pump. It just eliminates a ton of environmental variables, and that is exactly why it's the go-to method for high-volume, high-consistency manufacturing.
Now, comma bar, it's a totally different beast. This one is post-metered, and it's an open system. It's just mechanically simpler. You basically create a super precise little gate and just wipe off anything extra. This actually makes it way more forgiving if you have slurries with challenging flow properties, because here, the physical gap itself is the main control, not a sensitive pump.
Okay, so picking your method is one thing, but honestly, that's just the start of the story. Real success comes down to mastering this whole interconnected system of variables that control the entire process. This is where the real art and science of coding really happens.
Now, the most important thing to get here is that none of these variables live in a vacuum. They are completely, totally interconnected. It's less like a checklist and way more like conducting an orchestra. If your foil tension, let's call that the percussion section, is off, it doesn't matter how perfectly the slurry feed rate your strings is playing. One wrong note, even a 1-micron variation in the coating gap, can throw the entire performance into total chaos.
So that brings up a really interesting question. We talk a lot about the slurry, the fluid dynamics, but why is something as seemingly simple as the stability of the foil, what we call web stability, so foundational to the whole thing? Let's take a second to think about the mechanical forces at play here, because they're often overlooked, but they're absolutely critical. And tension control is the perfect poster child for this. It's literally the brute mechanical force that keeps that super thin foil perfectly flat and stable as it's flying past the coating head. Without that absolute perfect control, any precision you have in your fluid system is, well, useless. At the end of the day, you can have the fanciest coating head on the planet, but if that foil underneath it has a tiny wrinkle, game over. You're just making expensive scrap.
All right, let's talk about the two biggest dance partners in this whole process, feed rate and coating speed. It's pretty straightforward. The feed rate controls how much stuff, the massive active material, you're putting down, and the coating speed controls how fast you're covering the area. These two have to work together in this precise, unbreakable ratio, because together they determine the final mass loading, and that number directly translates to the energy density of your finished electrode.
So, what happens when that beautiful, delicate balance is broken? Well, that's when you start creating defects. And we're not talking about little blemishes you can polish out later. We're talking about permanent, irreversible flaws that will haunt that cell for its entire life. Understanding how they're born is the only way to prevent them.
And the cause and effect here is just brutal. It's so direct. If your tension control is poor, you get physical wrinkles. Simple as that. If your slurry feed rate fluctuates, you get patches of inconsistent energy density. And then you have what might be the sneakiest one of all, uneven or super aggressive drying. That can cause the binder to literally run to the surface, creating a weak, brittle structure that's just a ticking time bomb for failure down the line.
Yeah, let's zoom in on binder migration for a second, because it's a huge deal. This is not some surface-level cosmetic problem. What's happening is that all the glue, the binder, is rushing to the surface as the coating dries.
This leaves the stuff underneath, well, not very well glued together. It kills your adhesion, both particle to particle and to the foil. It basically guts the structural integrity of the electrode, and that directly murders its cycle life and its power capability.
So, if there's one word to take away from all of this, it's integration. The entire process has to be seen as one single dynamic system. You absolutely cannot tweak one thing over here without affecting everything else. Success only happens at that perfect meeting point of fluid mechanics, precision machine control, and thermodynamics. And remember, there's no going back. A bad coating is a bad cell, period.
Which kind of leaves us with this big question about what's next, right? The whole industry is pushing relentlessly for faster speeds and thinner coatings. So where's the next big breakthrough in control going to come from? Is it going to be from smarter fluid dynamics? Or maybe from machine vision that can spot a defect in real time? Or, and this is the really exciting part, could it be AI that can predict and adjust all of these interconnected variables on the fly? That's really the multi-billion-dollar question for the future of making batteries.